Welcome to day 30 of the 60-day AMA program. Here are the highlights from the session. Tonight, Jeremy will be discussing node operators, miners, storage, and data. Let's talk about nodes first. In BlockDAG, nodes can be classified by their roles and how they are deployed. Full nodes serve as the network's backbone, storing the complete DAG ledger and validating incoming data. Miner nodes engage in proof-of-work consensus, solving puzzles to create blocks and validating transactions while earning rewards. A BlockDAG node typically consists of two main components: an execution client that handles transactions and a consensus client that governs POW rules. Additionally, users can operate either mining nodes, non-mining full nodes, or relay nodes to handle traffic for external clients. For the current node setup scripts on the Awakening testnet, the hardware requirements are a minimum of 4 CPU cores, with 4 plus recommended for mining, at least 8 GB of RAM, and 20 GB of free disk space, along with additional room for chain growth and logs. A stable internet connection with good bandwidth is necessary. SSD storage is strongly recommended for high RPC call volume or longer history maintenance. Long-term node operation should also consider log rotation and disk monitoring. BlockDAG employs a peer-to-peer gossip model for block and transaction dissemination across the network. Nodes utilize TCP/IP for reliable communication and UDP for efficient peer discovery. Initial peer connections are established through a bootstrapping process in runtime, allowing nodes to expand their peer sets over time. Additionally, nodes conduct validity checks on incoming data to prevent the spread of invalid transactions. Now let's talk about mining operations. BlockDAG mining differs from traditional blockchains by allowing multiple miners to produce blocks simultaneously, reducing orphan blocks and enhancing efficiency. It employs multi-parent blocks that reference several previous blocks, thus creating a connected structure. Additionally, the BlockDAG protocol is utilized for consensus, enabling a consistent ordering and finality in the ledger. Tip selection in a directed acyclic graph, DAG, involves choosing the most recent unreferenced blocks, known as tips. This selection is crucial as it impacts connectivity, throughput, and security. Miners reference multiple recent tips when creating a new block, which enhances connectivity, minimizes isolated blocks, and accelerates the convergence to a stable order. Techniques like K-cluster analysis and blue set selection in BlockDAG help identify a well-behaved main set of blocks, leading to improved consensus outcomes through better connected tips. Mining incentives and security measures are designed to ensure that honest work is rewarded and attacks are costly. Rewards include block rewards and transaction fees for miners competing to solve proof-of-work problems, as well as EVM-style gas economics that encourage transaction fee payments. Security measures involve POW to deter consensus attacks, network layer protections like rate limiting and anti-spam filtering for DDoS defense, and DAG-aware finality, where blocks gain finality through later references, enhancing safety and reducing the potential for deep reversals. Now let's talk about storage and data management. BlockDAG utilizes LevelDB for local node storage, encompassing transaction history, DAG structure, and execution state databases. Full nodes validate the ledger and state, while miner nodes, in addition to validation, handle mining tasks. The official Docker setup maintains a consistent layout for persistent data and logs, essential for backup and long-running operations. BlockDAG mitigates blockchain reorganizations by emphasizing finality within a directed acyclic graph. Prior to reaching finality, nodes near the tip continue to discover new blocks and adjust ordering as the DAG develops. A block is deemed final when it is referenced by a sufficient number of subsequent blocks, rendering it immutable according to the protocol. This approach allows for rapid convergence and strong finality, where any uncertainty akin to reorganizations is limited to the most recent, not yet final segments of the chain. The mempool acts as a staging area for valid, unconfirmed transactions. Miner nodes collect these transactions from the transaction pool to include them in mined blocks. Transactions compete for miner attention based on gas fees, with priority fees incentivizing quicker inclusion. Transactions are broadcast and relayed peer-to-peer, maintaining a consistent view across nodes. Notably, with ERC 4000 337 account abstraction on the testnet, user operations enter a separate bundler-run mempool, distinct from traditional transaction flows. So in community terms, you can think of it as rapid convergence plus strong finality, where any reorg-like uncertainty is constrained to the newest, not yet final region. Now let's talk about EVM integration and performance. BlockDAG ensures EVM state consistency by requiring all nodes to execute the same transactions in a consensus-determined order, leading to a uniform final state. This is achieved through deterministic execution in a sandboxed EVM environment, allowing consistent results from identical inputs. The consensus mechanisms, Spectre plus Phantom, provide stable ordering and ensure atomic updates to EVM states. Additionally, the BlockDAG EVM is compatible with Ethereum tooling, having been rebased on Go Ethereum v1.14.11 with necessary updates for DAG-specific mechanisms. Developers access blockchain data through BlockDAG via EVM JSON RPC, HTTP, for reading chain data and sending transactions, and WebSocket RPC for real-time updates, which is beneficial for dApps and explorers. Network connection details, including chain configuration and official endpoints, are available in the Awakening Network Details page. Here's a checklist for practical operational considerations when running a node. Choose the appropriate role, mining versus non-mining, full validation versus relay gateway. Use Docker and automation scripts for managing lifecycle tasks. Configure wallets using EVM-style addresses, avoiding legacy formats. Ensure ports do not conflict and limit public RPC exposure. Manage data growth with regular backups and log rotation. And stay updated with dev releases for infrastructure enhancements and better operations management. In wrapping up, here are key resources for getting started. BlockDAG Docs, Gitbook, for architecture and developer guides. Awakening Testnet Node Setup, Guide for running a node. BlockDAG Client APIs, which include EVM, RPC reference, and WebSocket reference. Awakening Network Details for chain ID and connection configuration. And dev releases to track protocol and client upgrades. And that wraps up day 26.